Hello everyone, and welcome to another episode of Code Emporium, where we're going to walk through some more math. So in this video, we're going to relate the concept of mathematical concepts like random variables and probability distribution functions with machine learning. There's going to be a lot of math, and so let's get started. So let's start with the machine learning piece here and say that we want to construct a model. And this model is going to take in some inputs and outputs. So this model is going to predict the price of a house given some information. So let's say some of that information is, let's say, the number of bedrooms. And let's say that it is also square footage of the house itself. And then something else that we pass into it is the age of the house in years. Now, given all of this information into the model is going to predict a price at which the house should sell. Now, let's say that this model is going to be a linear regression model. And because of that, we can mathematically write out what the linear regression hypothesis would look like. So let's say that the price over here, which is what we want to predict, this is going to be equal to, I'm going to call the parameters of this linear regression model with the value theta. So let's say theta 3, this times the number of bedrooms in the house plus theta 2, this is another variable, or rather the coefficient of the variable square footage here, plus theta 1 times the age of the house itself, and then we'll also add in a constant intercept term, which is theta naught. And we will also add in an epsilon error. This is some irreducible error. Now, this entire equation over here is called the linear regression hypothesis. Now, the goal of this entire model construction over here, well, what we need to do is to find the values of theta 0, theta 1, theta 2, and theta 3. And we need to find these values given, well, the bedroom, square foot, age, and price of multiple houses that constitute our training data. And so, let's actually talk about how we construct our training data mathematically. To construct our training data, let's actually conduct an experiment. In this experiment, we're going to go to Zillow.com and collect our training data by looking at an individual house and then documenting all the features and the corresponding label, and then moving on to the next house and repeating the process. So for example, we go to Zillow.com, randomly pick a house. We have the first house. Let's say that this house has 3 bedrooms, and the square footage of the house is 3,025 square foot. And this is a 10-year-old house at a price of $757,000. Now, once again, we randomly go to another house on Zillow.com. This is house number 2. Let's say that this house now had 4 bedrooms, and it has 3,200 square footage of space. This is an 8-year-old house and its price is $800,000. And like so, let's say that we document these house prices for about 10,000 houses. And so now we have constructed our training set. Now that we have a bunch of observations in our training set, we can now start asking questions about these houses. So, for example, let's write questions as a heading. Now, one question that I would like to answer is, well, let's say, how many bedrooms was there in house number 2? And for this question, we are going to construct a random variable. So I'm going to call, first of all, let's say the outcome. We know the answer to this. Let's say the outcome of this specific question. I'm going to call it omega 21 because this is technically related to the house number 2, and it's going to be related to the first feature of house number 2. And this is 4 bedrooms. And the random variable here, let's call it x21. Now, random variables are functions that map the outcome of an experiment to some measurable quantity. And we could say that this is thus going to take omega 21 as input, and it's going to output just a number. In this case, it's 4. Now let's ask another question here about this data. So now that we got the number of bedrooms in house 2, what was the size of house number 2? So what was square footage of house 2? Similarly here, we are going to use the variable omega 22, the second house's second feature, and omega 22 itself is the outcome here. And the outcome, well, we observed it as being 3,200 square feet. And the random variable we're going to call now x22. And this is going to be, well, it's a function that takes omega 22 and then creates a number, a measurable quantity, which in this case is 3,200, which is representative of the square feet. Now, let's create a third random variable over here. And we're going to ask another question of, so what was the age of house number 2? And here, we are going to call this omega 23. And this is going to be, well, what we observe, which is 8 years old. And the random variable we're going to call x23 is going to take this outcome, omega 23, and map it to a number, 8. And let's say a final question for now that we want to ask here is which is, what is the price of house number 2? And this one I'm going to call just straight up omega 2. We don't have that as an outcome variable name. So I'm going to call omega 2, and this is $800,000. So that's 800K. And the corresponding random variable, let's call it y2. It's capital Y2 here that takes this omega 2, and it's going to be 800. I'm just going to leave out the thousands of dollars because typically these house prices are in increments of $1,000 in listings anyways. And so we have now taken an experiment, which is our training data set, and we're also now able to ask questions and get some quantifiable numbers from them with the help of random variables. And with random variables, now we can perform any kind of mathematics we want on them because we have numbers. So before moving forward with the actual probability theory and how this is related to that and how it's used to estimate parameters, let's actually classify each of these four random variables that we created here as being continuous or being discrete random variables. So in this first case, well, the number of bedrooms here, that's x21, it's going to be a count. And because this is a count, this is going to be a discrete random variable. Similarly, x22 over here, this is the square footage. Square footage is a measurement. And because it's a measurement, this is going to be a continuous random variable. We can have square footage that is also decimal points. And now for the third question, which represents the age of house number 2, the age of the house number 2 over here also is a measurement, and so can be a continuous random variable. And as 4, which is the price of house number 2, this can also be it's a measurement, and so it is a continuous random variable over here. Now, moving forward, though, we're interested in measuring the price of the house. And so we're going to be very interested specifically in this term, this price of the house number 2. Now, I created 4 random variables that each correspond to some observation that we made in our training data set. But in the same way, we can ask 4 questions and create 4 random variables for every single house that we observe in the training set. So if we observe 10,000 houses in our training set, we can create 40,000 random variables in kind of much the similar notation. And when we have all these random variables, we have all of these 40,000 numbers on which we can perform some mathematics to achieve our final goal of determining the parameters of a linear regression model that we're using to train. And so let's actually move to that next step of linking these numbers to some probabilities. All right, so the goal here is now to estimate the parameters of theta 0, theta 1, theta 2, and theta 3. And these parameters essentially are going to be the values that are going to maximize the probability of seeing our training data. In the last section, we saw training data, and we want to maximize the probability of seeing every sample, and hence compute the values of the thetas that maximize that probability of seeing every sample. And so what we want to do here is theta 0, 1, 2, and 3 is going to be the values with argmax. So it's going to be the values that will maximize the probability of seeing our data sets. So that's going to be maximizing the probability of y1, this is random variable y1, being equal to some value that we observed in our training data set, which I think was $757,000. And then we have y2. This is going to be another value, which we saw is $800,000. And so on until y10,000, because that's the size of our training data set and the number of observations that we have. And all of this is, such that, we assume the values of theta 0, theta 1, theta 2, and theta 3. Now, I'm also, for the sake of completion of notation, going to write under argmax theta 0, theta 1, theta 2, and theta 3 here too. Now, this is clearly very cumbersome notation, writing all of these thetas, and so I'm going to simplify all of these thetas by creating a vector, a theta vector that I represent as just capital theta. In this case, I'm going to recognize this as theta hat MLE because it is the prediction that we make of theta, and MLE stands for maximum likelihood estimation. And this hat means it's a prediction. So something to note here is that this P, this capital P, is a probability distribution function. But it's a probability distribution function over a continuous random variable, specifically y1, y2, and capital Y 10,000. And since these are continuous random variables, this probability distribution function is more specifically called a probability density function. Now in the next section, we're going to replace this notation to represent a probability density function, as well as look into the concept of independently and identically distributed samples and what it means to this equation mathematically. So first, samples are independently distributed. This means that for every house sample that we have taken, the price of the house is independent of the price of all the other houses in our data set, which is a very reasonable assumption to make. And because of this assumption, the joint probability can be represented as a product of probability distributions. Going to write triple dots over here since it's a product of 10,000 terms all the way up to y 10,000. And that is equal to the small y 10,000 given the value of theta. All right. So now we're also going to replace this more generic notation of P, which is the probability distribution function, with a probability density function, since we know that each of these are, well, they are continuous random variables. And to represent a continuous random variable, we typically use the notation of F followed by a subscript of that random variable yi. And so let's see how that looks here. So theta hat MLE is going to be equal to the argmax over theta, where we take the first term as F. Now the subscript is going to be y1, since that's the random variable over which this probability density function applies. And it's going to be a function of the value that it can take, which is the small y1. And this is going to be given theta, as usual. And we write this for the 10,000 terms. So now that we have an understanding of what independent distribution means, we'll also look at the second part, which is identical distributions. And when we say that data is identically distributed, well, in this notation, we see that there's 10,000 different probability density functions that we're taking a product of. But in reality, all of these probability density functions can be assumed to be the same. What this means practically is that the probability that house number 1 that you choose is between $700,000 and $800,000 is equivalent to the probability that house number 2 is also between $700,000 and $800,000. And this is the same for every single house. And because of that, we can kind of write all of these individual probability density terms as just being the same representation, f subscript y. And so I'm going to do just that. Samples are identically distributed. And from mathematical notation standpoint, it'll be the exact same as the previous statement that we wrote right here, but we are only going to change the subscripts so that they all match each other. And so this is also going to be a subscript y, but of the same y2 variable. And even for the 10,000 term, well, it's the same y. And so I hope it's clear why the independent and identically distributed assumption that we typically see in machine learning actually is very useful in just simplifying the mathematics itself. So let's write this in a much more concise form with product notation. So that's theta hat MLE. This is going to be equal to argmax of theta. And we're going to introduce the product notation over here, which looks like a huge pi symbol. And I'm going to say the iterator is going to be I, that goes from 1 to 10,000, since that's how many training samples we have. And it's going to be f of subscript y. And what's being iterated is specifically, well, yi. And this is given the value of theta. So this here is actually a very good generic endpoint that, depending on the machine learning model and algorithm that we are considering, we would simplify this further, because that would require different assumptions of this probability density function over here. Now, in this case, we had a linear regression model, and for linear regression, we typically assume this to be a normal distribution. So let me write that out. For linear regression, the fy term is assumed to be normally distributed, where the mean here is actually the mean prediction of the model itself. So let's assume that to be represented as yi hat. And the standard deviation I can just let to be, well, sigma. And so we write sigma squared for variance. And if you substitute this value over here, and you kind of expand this to be, the probability distribution or density function of the normal distribution, then you will see that the value of theta is the value that is required to minimize the residual sum of squares. So let me actually write that out more concretely over here. So what this means is that this theta hat MLE is going to be equal to argmax of over theta of -1 times sigma, where I ranges from 1 to 10,000, of like y I, this is the actual value, minus the, let's call it again now, yi hat, which is a predicted value, whole squared. And this term over here, this term here, is the residual sum of squares, because the error is a residual, that is yi minus yi hat. It's a sum of those residuals and the sum of squared of those residuals. So residual sum of squares. Now, how exactly you get from this term to this term, I'll probably leave it to you as an assignment for now. But the hint is that you just need to replace this term with the normal distribution, considering the mean as the prediction and y as some constant sigma squared. And if you take logarithms on both sides, technically the value that maximizes the logarithm is also the value that maximizes the function itself. You will end up with this expression over here. And we can write this out as arg min of the sum of residual squares as well. So what this implies is that the value of theta that is optimal for our machine learning model is the value that minimizes the residual sum of squares. And I hope this also explains why you see the residual sum of squares so often, especially associated with linear regression and basically a lot of these other algorithms that rely on the normal distribution itself. So thank you all so much for watching. I have a related blog post in written format of everything that we've covered here and also the last 5 videos just in a blog post that should be in the link down in the description below, posted on Medium. So please do follow me for updates on Medium there, as well as on my channel here. And I appreciate the support. Thank you all so much for watching, and I will see you in another one. Bye-bye.